Okay, so sharing my screen here, and I thought I would, instead of diving right into DZmix, program that Joel and I made a few years back that does a lot of what does some of the methods that Sam talked about. I thought I'd first give a short little PowerPoint, maybe like 5-7 minute PowerPoint, just to kind of set up the problem here. And so this might have a lot of overlap with what Sam talked about earlier. Again, I missed his first hour or so of his talk. So what we're trying to do in this is just a simple geological example. Just imagine some kind of source to sink system. You guys give me a thumbs up. Joel, can you see what's going on? Cool. Okay. Yeah, imagine that this kind of rugged mountain. Excuse me?
Full screen?
Full screen. Got it.
Oh, or does that screw you up? I forgot.
It doesn't matter. I'll put it on full screen. How about that? Can you see that?
That works.
Great, thank you.
Great. Okay. Yeah, so let's just imagine that we have some source to sink system here. And this and the source terrains are characterized by 3 very different age distributions. So source A, source B, and source C. And these are just some eroding mountainous terrain. And those sediments and detrital zircons are being deposited in some local basin. And so we're going to call this our mixed sample here. So this mixed sample is some combination of sources A, B, and C, right? And the question is, okay, we have some geologic question, but we want to know how much sediment came from A, how much came from B, and how much came from C. Okay, so this is where the Monte Carlo mixture model comes in. So the Monte Carlo method, that's core is pretty simple. You take a system that can be described mathematically, and you introduce random variability into that system, and you see if you learn something about that system. And so for us, the random variability is randomly mixing sources A, B, and C to come up with hundreds, thousands, or tens of thousands of forward models to compare to this mixed sample. And then we will use the quantitative metrics that we've talked about earlier in the course to figure out what are the best mixtures, and then see if we learn something, right? And so, for example, if we just took one, call it a trial, right? A trial mixture, we just randomly assign 55% of source A, 4% of source B, and 41% of source C. And here, this is a little different. What I'm guessing Sam talked about earlier, we're not taking 55% of the ages out of this distribution, but rather we're scaling this distribution down to 55%. The whole distribution and that assumes that this is an accurate representation of the underlying population of A. Now DZmix, I'm not going to go over it, but the capabilities are built in to randomly pull ages out and create distributions from individual ages. But what I'll talk about, mainly because of time constraints, we'll be using distributions that are scaled down to these different weighting proportions. And these proportions have to add up to 100%. Let's see if I did that right. Yes, these add up to 100%. And you add these together and you get some model distribution, right? In blue here. And so our model distribution, the goal is to match that mixed sample, that basin sample that is indeed some mixture that we don't know. And you can see this is the cross correlation coefficient that Joel outlined earlier. And 0 is the worst fit that you can get. 1 is a perfect match. So clearly this is a pretty bad fit. And let's keep track of these results here. This is kind of a weird looking plot, but what we're going to do is plot the results and try to visualize what's actually happening in this Monte Carlo method. So we have percent source contribution from 0 to 100% for each of the different samples here. So source B is 4%, so 4% there. Oops. Source C in the cyan color, so it's 41%, and 55% for source A. And that combination there gives us an R squared that's really low, so 0.05. We have R squared on the y-axis here. And our goal is to get to a perfect fit of 1. Okay, and so if we take another random sampling, or rather a random weighting of these 3 sources, so 45, 38, 17%, you can see that that gives us a little bit better of a fit. So like still it looks pretty bad at the lower end of the age spectrum, but we're starting to sort of match this middle part. R squared is a little bit better with this combination here of 17, 38, and 45, giving us an R squared of about 0.3. And so with the Monte Carlo approach and modern computational power, we can do this tens, hundreds, thousands, hundreds of thousands of times until we find the best fit possible. And because these are synthetic data that I just made up, there is indeed an answer here that has a perfect fit. Okay, and that answer is 10% of source A, 80 of B, and 10 of C. And that kind of makes sense, right? Because B looks a lot like that mixed sample with this big, sort of call it a Grenvillian age distribution. Okay, or an age group. So we have 10% of sources A and C, then 80% of B. And so that top part of this plot is the answer for your source contributions. And so if you have, I'm not going to go through every step here, I'm just going to jump to the answer. If you have a lot of different potential sources, you may not get that perfect fit, right? And this really kind of speaks to reality here, right? Like when we go out to a basin, then we characterize sources, what are we actually going to get? We're going to get some envelope around that mixed sample if we're doing good, right? If we have actually characterized these potential sources appropriately. And so here again, we have our potential source contributions. And in this case, we're going to take the best 1% of model fits. And that's how we're going to put some uncertainties on these different potential sources. So again, we don't get a perfect model fit, but instead we get a range of model fits. And I think this speaks to what Sam mentioned a little earlier is, and I think Glenn reiterated, is if you just take that one single fit, you're not really looking at the range of possible results. I think I have, yeah, so again, this is synthetic data, so there is a perfect model fit that we can get to using an optimization routine, like that minimization function, the objective function that Sam went over. So it is possible, but this is perhaps less informative. That one best fit is less informative than the envelope around it in terms of interpreting something geologically. Okay, and that's just a picture of DZmix that we're going to open up now. So while I open up DZmix, are there any questions about the model setup or what we're trying to do here? Basically, unmix this basin sample based on known or, well, perhaps hopefully known characterized mixtures as best that we can know them. Okay, not that I'm going to move on, and this will be one of the hands-on parts of the course, and so I'm going to take this pretty slowly, right? So if you've downloaded the material, you have an application for DZmix. I'm running on a Mac, so I'll open up the Mac application. If you're running in Windows, you'll have an executable, or if you're running it in MATLAB, just run the dzmix.m file. If you're on Catalina and Mac, the application won't work, and I apologize for that. There were some, yeah, there were some issues, rendering issue arguments that were going on politically with those different companies. So Catalina didn't work that year. But I'm going to open up the application and run the application. And while that's opening, I'm going to open up one of the input data sets and explain what is going on here, how you actually input the data. Okay. So here, these are our 3 input potential sources, kind of like this source A, B, and C, or 1, 2, and 3 from the, PowerPoint. And this would be our basin mixed sample, target sample, whatever you want to call it. So you can have as many sources as you want. You could put hundreds in here. You're only limited by your computational power. That said, if you're going to run one of the optimization routines, you really don't want to put too many in here because it gets computationally very intensive. Okay, so what you're trying to unmix, and then your potential sources, and yeah, again, you can have as many as you like. Okay, please slow me down, or if there's, just say in the chat, like, hey, slow down, please, and then maybe one of the other course leaders can wave me down and tell me to slow down. Otherwise, I'm going to keep going at about this pace. Okay, so like pretty much all of the GUIs that Joel and I have made to date, there's a browser window in the top left, and that's how you're going to select navigate to a file. So mine lives on the desktop in that application folder. I'm going to select the input data simple synthetic. So this is basically the example that I gave in the PowerPoint. Just select open. Okay, so you have a couple of options right away up here. So the number of trials, that's how many times you randomly weight your potential sources. So if say you, I should note that I'm not going to follow the step-by-step guide here exactly. That's more for everyone's reference after the course, but I'll go over something along those lines. So if you're trying to follow along point by point, I'm not looking at that. I'm just looking at the DZmix screen. So just heads up. So yeah, if you just take, say, a random 100 weightings and take the best 1% of fits, you can run the Monte Carlo model. And this will be a pretty short model. 100 was apparently too few. Let's go with 1,000. And you can see similar to what to the bootstrapping examples that Sam showed, you get some envelope around these plots. So I should explain these a little more. Let me get this out of the way. Okay. In the top here, you have probability density plots and cumulative distribution functions. By default, it plots probability density plots, but you can use kernel density estimates with this parameterization on the left here. So I'll go over that, and we'll test that in just a minute. But for this example, we're using probability density plots with the comparison metric of cross-correlation, and then cumulative distributions for the Kuiper and KS test. I should note, if you're on Mac, this color bar doesn't really make a whole lot of sense over here. It should have 1, 2, and 3. I believe that's debugged on the Windows versions, but on the Mac version, the numbers here are pretty meaningless. It should be 1, 2, and 3. Compatibility issues there. Okay, so let's, typically 1,000 is not really enough random weightings of the sources. By default, we put in 10,000. If I'm really happy with some results and I've verified that it actually makes sense geologically, I'll usually bump this up to even 100,000. For our simple testing today, I wouldn't recommend doing that. 10,000 is probably enough for what we're going to do. And so I'm going to run this again. And what you'll notice is that these envelopes around the data will look a little bit different as we're testing more and more random weightings and taking just the 1% best fits. And so we have the 1% best fits. That's going to plot 100 out of what, 10,000, if I did that math right, comparisons to that mixed sample or that basin sample. So it takes a little longer to go to 10,000. But now you see you have a nice kind of a swath of data around this. And the things that you really want to look at, I think Sam gave an example earlier that I missed, but you want to see how well the fits, how well you actually fit that mixed sample based on your input sources. So an R squared of 0.998 plus or minus 0.001 based on, again, on those top 100 or 1% fits, I'd say that's pretty darn good. And 0.02 for the Kuiper V value, or 0.02 for KS test D statistic, those are incredibly close fits, and we can see that visually too. So that's one thing you want to look at. How good was the model fit? And in the next example that I show, this will become clear why this is super important to think about. The other thing you want to look at is the relative contributions. So based on this model, it says, okay, well, we have 20% of source 1, 70 of 2, and roughly about 10 of source 3. And this should add up to about 100%, right? Or 1 for relative contribution. And some standard deviation, again, based on those best 1% number of fits. You can plot these relative contributions here. And again, if you're on a Mac, the color bar is not really going to make a whole lot of sense, but you can see that we have sources 1, 2, and 3, just numbered on the x-axis, and the relative contribution, their relative contributions to that mixed sample based on the model results on the y-axis. So 20% of source 1, 70 of source 2, and 10 of source 3. And something that again, I think is really important is now, well, we have this result from using probability density plots, but the reason Joel and I included all 3 of these different metrics is because sometimes you get different results. And here, because these are very simple synthetic data, the Kuiper test gives pretty much the same result. So 20, 70, and 10. The KS test D statistic also gives a very similar result. Okay. Maybe I'll pause there before diving into the next example. Are there any questions out there? I'm not seeing the chat function as I present this. Maybe we've put people to sleep.
There was a question. It looks like has answered it. Other than that, I don't see any questions in the chat box.
Awesome.
Actually,
Okay.
There's one here. Can you explain what percentage best fit means? Why is it 1?
Percentage. So up here?
Yeah, that guy.
Yeah. So actually, the way to do that is to go back to this PowerPoint. So we'll go to the simple version. So say if we randomly chose, say, 10 different source mixtures, then the best fits will plot toward the top. We're taking the best 1% of how many we ran. And so here, if we only ran 10, that wouldn't be enough to actually answer that question. But if, say, you ran 100 or 10,000, you could take that top 1% of fits, which would be 100 of these results. And so if you have, say, 10,000 trials, and you said, well, I want the top 2% fits, then it's going to plot 200 of the best fits that you get just from the random weighting in comparison to that mixed sample. Did that answer wherever that question came from, whoever had that question?
It looks like there is
So
a
it depends on the
follow-up.
trial number or on the number of trials.
Sorry, there were 2 people speaking at once. Can you repeat that?
Go for it, Joel.
There's a follow-up question. So it depends on the number of trials.
Yes, absolutely. The number of fits that you actually keep to calculate the different relative contributions and the best, how well your model fits, that depends on how many random weightings you attempt, so how many trials, and what percentage of those attempts do you want to keep. So we only keep the best, say 1% or 2% of model fits to then produce these different plots and to calculate the relative contributions and how much they vary based on standard deviation.
Bert, why don't you just do a quick trial where you do 100 models or 1,000 models and keep 50% of them?
Let's try that. Yeah, maybe that'll be a little clearer. There you go. Okay, good call, Joel. Okay, so here we've randomly weighted sources 1, 2, and 3, 1,000 different times, and we're plotting half of those. So what this really does is it shows you how much it's exploring the sample space based on the input potential sources. And so by taking and keeping fewer and fewer, or lower and lower percent, so fewer and fewer results, it'll start to collapse that envelope around that mixed sample. So here we're keeping fewer and better fits. So that would be 20%. So of those fits, if we take it down to 10 and run it again, you'll see that we're going to collapse that window even further because we're keeping better and better fits. Yeah, that's a really good visualization of that. Are there any other questions?
I'm not seeing any right now.
Cool, so let's dive into, I'm gonna close this. Let's dive into, I'm gonna look at the step-by-step guide here, just to get a picture of what I'm going to talk about. And so this next data set comes from a paper that Joel wrote, I believe as a postdoc. What we're going to do is our mixed sample now is going to come from a small drainage basin in Colombia. Okay, and by small, I mean, here's a scale bar of 20 kilometers. And so what Joel and colleagues did is they went to this watershed, this drainage basin here, and this one here, and they said, okay, I'm gonna go down to this, there's a modern river down at the base here at the trunk stream, and they collected some sand. Because presumably that modern sediment should, the detrital zircons in that modern sediment should be some mixture of the different potential sources in this drainage basin. And so what they did to characterize this drainage basin is they went and they collected samples from the different stratigraphic units to characterize those different potential sources. Okay, so the goal is to unmix these this basin modern river sample from this drainage basin based on these potential sources within the basin, within the drainage basin based on the rocks. So that's the model setup. So we'll go and find that data set. So just hit select file again. And so it's the Rio Cusiana data set here that I'll be uploading. So I'm going to dial this back to not 0%, how about 1% of model fits. I'm gonna take it back up to 10,000. Oh, I have to go select the file again. Okay, and it's ready to go once you see these plot up here. And before I run this, what you'll notice is this, there's some very young dates here, and we're using probability density plots in this, based on this parameter here. So one of the things that I want to test is probability density plots versus kernel density estimates for our results. Okay, and so let's run this model. So this will take just a second. So what I'm looking for here, whenever I'm running this model in my own research, is I want to see consistency, and I want to see consistent results that are geologically that make geologic sense, no matter what I do no matter how I parameterize this, whether it's PDPs, KDEs, and whatever mixing coefficients I get out of these three different metrics. Because if they're wildly different, that's informing me that something might be not right in my model setup, and the results might not be that geologically meaningful for what I'm trying to test. So again, I know we're harping on that point, but it always comes back to the rocks, right? Okay, let me close these old windows here. And so the first thing I want you to notice is down here, how well did the model do, right? And so 1 is a perfect fit, a 0 is the worst fit. 0.75 is not a great fit here. And you can see that visually, right? So based on the model input, the potential sources, the different mixtures, the closest they can get are in blue. And you can see that those are pretty different from the mixture that you're trying to unmix in black, particularly at this about 1,400 million year time interval and at this lower end, right? So you can see that it's not a great fit based on the cross correlation coefficient in comparison of PDPs. The CDF curves, the cumulative plots, they look a little bit better. You can see that distribution is indeed falling within that kind of swath. Your mixed sample is within that swath for the Kuiper test, and it falls a little bit out of that swath based on the KS test. And so what I like to do is look at the relative contributions, right? So I want to say, okay, well, let's plot up the contributions from each of these different metrics. Sorry if it's getting loud. There's a bunch of loud planes flying over my house right now. It's kind of deafening in here. Okay, anyways, so from left to right, we have cross correlation coefficient, Kuiper test, and KS test D value. And what you notice immediately is that these do not give the same result. And these are different results based purely on the different comparison metric that we're using. So KS and Kuiper, these are always pretty simple. As Joel went over earlier, these will generally give similar results. So I want to just focus on these two. Okay, so what's going on here, right? What you can see is that the cross correlation coefficient identifies this sample here, this 2-bug 190 sample, as perhaps a more significant contributor to that modern river sediment, and also AM7, whereas that's not the case based on the Kuiper test. And the other thing that's drawing my eye here is that these error bars here are pretty large for the cross correlation, and what that really tells, the way I interpret that is due to non-uniqueness. Basically, there's multiple solutions, and so there could be a number of things wrong here, right? So there are a number of reasons why this might not be a good fit. Now, let's go back to that. Go back to the geology here and say, okay, well, why wouldn't we get a good fit? Well, perhaps one of the input sources, AM6B here, maybe there's some along strike heterogeneity here. Maybe that sample that was analyzed is actually not representative of whatever formation it was supposed to represent. Or perhaps maybe Joel and colleagues in their data mining and the samples that they analyzed themselves, perhaps they missed a unit. This is a really jungly area, I'm aware of that. And so perhaps they missed a particular sample or a source formation, right? And so the model actually can't get to better solution because the data simply aren't there. Like the old saying, this is a great data set, but garbage in, garbage out, in the sense that if your model doesn't have the proper input data, it's going to be a meaningless result, right? So again, it always comes back to the geology. For this particular study, it was really a cautionary tale when Joel and I revisited this in 2017 for the mixing paper. Like, well, you know, all of these samples were characterized by relatively few grains, so what we would call a low N sample. So some of these are characterized by only 70 or 80 grains, which nowadays, because of advancements in methods for LAICPMS, that's a pretty low number, and you know the costs have decreased precipitously, and so now people are analyzing 100 to 300 grains, sometimes even thousands of grains. So I bet if we went back and even just reanalyzed those samples and got a better characterization, that our model, we would get better model fits just based purely on the size of the individual samples. But also, I think there really must be, with that low of a cross-correlation coefficient, there must be something, a source missing. That would be my, my interpretation here. But again, taking these results, not saying that these are the actual contributions, but rather saying, well, we don't have a very good model fit here. What is that telling us geologically? And the interpretation is that, again, perhaps maybe we've missed something in our model setup and our sampling scheme. So I'm going to pause there because I have one more data set that I would like to go over, and then we can do some tests with kernel density estimates and whatnot. Are there any burning questions out there? Is this thing on? Okay, if not, I'm going to go to the next data set and we can play around with some of these other parameters. So when Joel and I were writing this paper, little did we know, people were working on this problem, Glenn and Sam included, but Alexei Leach and others were also working on these mixing problems. We were all kind of working in parallel, and I don't think any of us knew it, but we were actually all working on this stuff. So it was kind of fun to all converge and land in the same place. But what Alexei did in his 2016 paper is he compiled data from central China. So this is the Tibetan Plateau right here. So this is a huge area. I call it a mega regional area. So that's 500 kilometers there. And what he did was he defined 4 different potential source terrains. So the Moose, the Central Deserts, Chadian Basin, and the Yellow River here. And his big question was, okay, where did the zircons in the Luss deposits? Luss is just a silt-sized wind-blown dust. You can actually get zircons out of those and analyze them, even though they're super small. But his question is, okay, where did the dust come from, and how much came from each individual potential source terrain? Okay, so it's in one way, it's a simpler problem in that there are only 4 sources made of huge compilations of data. But it's also just regionally, it's a more challenging problem, I think, because this is a huge area. This is thousands of kilometers shown on this map. Okay, so let's see what we get. Okay, let's do some tests on Alexei's data compilation. So we're going to load in the Luss Plateau data set here. I'm going to clear the plots, just a little bit of housekeeping. There we go. And I'm going to do the same run. I'm going to start with probability density plots. I think I have about 10 minutes or so left on this module. So we will play around with these different parameters as time permits. Okay, so again, we have our input data. So the black line that's going to be the Luss Plateau. That's what we're trying to unmix. And then these colored samples are our potential sources. Same with the CDF curve. One thing to note as this is running, if you are running, say if you do try to run 100,000 or more, right now we have the parameters down here set to, if you can see my cursor in the bottom left, basically the threshold cutoffs. What it's doing is it's storing every single test. So it's storing all 10,000 tests. But if you know that you're going to get results that are generally pretty good, like see here you get a 0.9, you can set that threshold cutoff to say, well, you know what? Set that to 0.5, for example. Anything below 0.5 cross correlation, just throw it away. I don't care, right? And same with the Kuiper test and KS test. You can say 0.5 and say anything above a 0.5 would be a terrible fit. I don't care. I don't want to see it. And that's a way that you can increase your computational capabilities. Because if you start to run at 100,000 tests and you're keeping everything, depending on the machine you have, it might start to bog down and it might even stall. So just a heads up, these are parameters that you can play around with to disregard what you know are terrible results. Okay, but we didn't get terrible results in this example. So here you can see, again, first check how well did the model do. So 0.9 is a pretty good, it's a pretty good fit, right? And you can see that visually. Right, it's a pretty tight window that doesn't use some of these visualization tools up here. You know, it doesn't land perfectly, but it is close, right? And considering the mega regional scale that we're working on, I think this is pretty amazing that that you even get as close as you do, particularly in these more prominent age groups here. It's pretty astounding that you can even get that close. Again, we're working on the 1,000-kilometer scale here with these data compilations of a few thousand grains per sample. Same thing goes with the excuse me, the Kuiper test and the KS test. You can see that these are pretty good results. You're approaching 0 there, right? And now if we plot the relative source contributions, again, here what I'm doing is, let me get rid of some of these. Some more housekeeping, is I'm looking for consistency here. I want to see that the CDF-based metrics, and we know that these are generally going to be pretty similar, so I'm just going to plot one of them. You can see that even with these generally good fits, you get a little bit of variability in your model results. The cross-correlation coefficient, it says, well, hey, I think there's 30% of the central deserts and 60% of the, whatever red was, the Mu'us, I think. Yeah, the Mu'us. And the Kuiper test is saying, well, I think it's mostly Mu'us as the sediment source to the Loess Plateau. So again, this is a better model result, but it's not perfect and it's not as consistent as it could be. Okay, so what you can do now is test, well, we say, hey, well, maybe it's because there are these spiky ages down here with the probability density plot. There's, you know, that's one of the kind of knobs that we can tweak. So now we can just say, well, let's try kernel density estimates and see if we get a more consistent comparison, or more consistent rather result for the percent contribution to the Loess Plateau. So I usually start with about 15 million year bandwidth. It'll plot it here, so I'll know if that's, you know, reasonable. Let's clear these plots, and I'm going to go ahead and run this. And it's gonna replace that the PDP now with a KDE, or KDEs of the mixed sample and the potential sources. And you can see that with a 15 million year kernel bandwidth, that it does indeed smooth this out quite a bit. And something that I didn't mention earlier in the very first presentation this morning, another reason that I like using kernel density estimates is, if I'm going to be looking at these kinds of probability plots, is if you're compiling data from, you know, dozens of authors, then it's not always obvious. Oh, that didn't work. It's not always obvious how they've reported their uncertainties there. And so it's weird, it failed for some reason. And so a KDE is actually oftentimes a better way to go, just because you don't know how these different authors replaced their or reported their uncertainties.
Kurt, I think you've put in the cutoffs backwards.
Thank you. I was like, man, I tried this morning, like before everything, and it all worked. Yeah, so what happened there? Thank you, Joel. Good catch. I was basically saying, if anything, yeah, it had to be a perfect fit in order to keep it for both cross correlation and Kuiper and KS. So that's I got those backwards. The second copy isn't quite doing it yet for me. So yeah, the test here is to see if we get a considerably different result from PDPs to KDEs. And again, I want consistency from no matter how I tweak these parameters, unless they're wildly different. But PDP and KDE should give generally similar results. And so if they don't, then that means there's something going on with the model setup. So let's have a look. So that looks a little wild, right? Do I still have it? No. Okay. So now this is interesting, right? So remember the Kuiper, or the Kuiper test before said, okay, I think it's mostly mootness that is contributing to the Loess plateau. Whereas the probability density plot, it said, well, no, the central deserts were at least 30% of that. But now using kernel density estimates, you can see that you get a more consistent result. Okay, and so that's an important point. So what that means is, well, perhaps there's something, and my go-to with a probability density plot I'm going to call it out as a problem, is very, very spiky young ages, because you have a low uncertainty for those. So for some problems, they work just fine, but for this particular problem, it was resulting in considerable inconsistencies among the different metrics. So here I would say trust these results a little bit more, because in that they are just more consistent among the different metrics, right? See if the KS test says the same. It should, because the Kuiper is usually pretty similar. And so yeah, that's a nice result there. So I would be more confident in these percent contributions than just picking the cross correlation based on the PDPs, because that was, as we have seen now, is kind of the outlier in terms of results. And then of course, as we've all been harping on today, take it back to the geology and see if that makes sense with independent observations. And like Sam mentioned, it's something geologists actually do quite well, is we take in information from all different sorts and we attempt to synthesize it. And I think we actually do a pretty good job of that. So not to promote geologists too much, but hey, we're all here. Okay, so there's a couple of minutes left here. It's 1:28 according to my clock. Are there any quick questions, thoughts, discussion points? Hopefully that was coherent a little bit.
We have a question from Peyton.
Yes.
So an ideal scenario would be that all three tests would have similar results.
Absolutely. That would be, that again, and I do this not only with mixture modeling, but I do this with multidimensional scaling. I do this with DZ stats. I look for consistency among the metrics, because that's telling me that it's not the model. If they're consistent, it's telling me that it's not something in the model, right? Or the comparison metrics themselves. If they're consistent, that gives me more confidence that that it is indeed telling me something. So mixture modeling, non-negative matrix factorization, as Joel's going to talk about, and Glenn, you're going to be in on that as well. MDS, I look for consistency in all of among the metrics. And if they're different, then you start doing the other thing that geologists do so well is do your detective work, right? Figure out why it's different.